So our first speaker for this session is Geoffrey Ndu, and I'll let him take over.
My name is Geoffrey Ndu. I'm with the University of Manchester. I'm going to talk about the benchmarks we're creating for OpenCL FPGAs. So it's work in progress, so your criticisms and suggestions are welcomed. So the talk is going to follow this outline. So I'm going to give an overview of FPGAs, because most people here don't have FPGA and hardware background. I'm going to talk about compiling OpenCL to FPGAs. Then I'm going to talk about the benchmark. Then I'm going to talk a little bit more on a case study we did, which is if you take OpenCL code running on CPU, how is the experience compiling it down to FPGA? How does it compare to compiling on CPUs? So the benchmark is called CHO. It doesn't actually mean anything. So it's freely available online on GitHub. So there you can also see 2 papers that go in depth into FPGAs, compilation of software languages to FPGAs. And it's developed as part of AXL project. AXL is an EU-sponsored project, European Union-sponsored project. It's called AXL, means Advanced Analytics for Extremely Large European Databases. You'll be asking, why are we doing FPGAs? Well, we're doing FPGAs because the mandate of AXL is to speed up large volume data analytics. So one of the things we're doing is running database algorithms on FPGAs using OpenCL. We use other software to hardware compilation tools like C and CHO and other types of software to hardware compilation. So why do we need to create our own benchmarks? We looked around for something open, but we couldn't find any. Software benchmarks, basically the ones for GPUs, are often too large and complex to compile down to FPGAs. So I believe anyone knows the importance of benchmarking, so I won't delve into that. So what is an FPGA? So an FPGA basically is a sea of lookup tables. So a lookup table is basically high-speed memory. So if you have a truth table that looks like this, what you just need to do is to load the outputs of your truth table into the appropriate memory locations in your memory, such a way that if you give the inputs of the truth table as addresses of the memory, you should get the appropriate output. So this one is 0, 0, 0. Then you should get a 0 because it's address 0, and you already start 0 there. So that's basically how FPGAs work. So technically, FPGAs are not hardware per se. So in modern FPGAs, it's a little bit more complex. So your lookup tables plus other circuits make up what is often referred to as logic cells. And the group of logic cells make up what is often called the logic block. And the logic blocks are connected to one another using a reconfigurable network. So if you have a very big or complex digital function, that is how you implement it. So FPGAs also have other things on it, so like the DSP blocks, which are basically multipliers. You have BRAMs, which are basically RAMs distributed all around. You have communication interfaces like the PCIe Express, Ethernet, and other types of IOs. So how does FPGAs outperform CPUs and GPUs? Okay, assuming you have a simple thing like bit reversal on ARM9, which don't have the bit reversal instructions, no matter how you optimize it, you're going to spend at least about 48 cycles. But on an FPGA, you can basically just reverse the connection between two buffers, and assuming the processor and the FPGA are running on the same clock speed, that's a lot of speed up. So that's basically how FPGAs outperform CPUs and GPUs. So how do you compile down something that's basically a software language into FPGAs? So a typical compilation chain looks like this. So you have a software compiler, but the difference is that you don't produce machine code anymore. You produce what is often referred to as hardware description language. So hardware description language is things like Verilog and VXDale. They are low level that you can specify what happens on the clock cycle. So they're often difficult to program in. So we take a typical compiler, you emit Verilog, or another high-level hardware description language. You feed it into synthesis tools. So synthesis tools at a very high level are compilers that compile to FPGAs and hardware. So at the end, you get an FPGA configuration, which is basically what programs the FPGA to do what it intended to do. So back to CHO. As I said earlier, is work in progress. So currently, it's a part of CHStone. So CHStone is the popular C to FPGA and to hardware compiler. So HLS, as is often referred in the hardware world, is where you now use software languages more or less and use it to produce things like hardware descriptions for your chips or produce bit configurations for FPGAs. So basically, HLS is describing FPGA design as if you're doing software. So it's often easier to do than the traditional FPGA and hardware languages. So it's easier to write than Verilog. But often you trade off usability and productivity for quality. So currently, CHO has 12 diverse and non-trivial applications. I'm going to show later how non-trivial they are. It's currently written in OpenCL tax parallel model. So because we took a C benchmark, I also wanted to be able to compare C and the traditional, we wanted to compare OpenCL and C compilation as well. So we didn't bother parallelizing it. Again, the CHStone benchmark is kind of not what you usually use OpenCL for. So I'll show that later. So we have 12 applications. So they could be grouped into arithmetic, which are basically implementations of things like double precision, floating point addition, division, multiplication, and sign. Then you have the ones on the media, which are things like JPEG. And you have cryptography, which are your cryptographic algorithms like Blowfish and secure hash algorithm. And then you have this one, which you can argue is a state machine, but it's a simplified MIPS processor. So we needed to characterize the applications in the benchmark. What we did was to build a Clang tool. Clang is the front end for LLVM. So we built a tool that worked the abstract syntax tree. Basically, what it did was to classify all the nodes it finds. So basically, the useful why this is useful is that some operators are expensive on FPGAs. So things like divide, multiply, you want to reduce them as much as possible. So these tools helps to show for the various applications, which one are complex in quotation marks. So this is what the source level characterization looks like. So the kernel basically are the application. So the type is basically the dominant type in each one. The lines of code is the lines of code in C. The functions are the number of functions. Remember, this is all OpenCL. You have the variables, whether the scalar or aggregate. Then you have the type of statements you have there. You have the operators as well. So you can see some have plenty of multiplications and others don't. So basically what this says is that the applications are not trivial. We also did characterization at the intermediate representation level. So most OpenCL to FPGA compilers we've seen do the actual translation from software to hardware at the intermediate representation level. So for example, LLVM intermediate representation is low level enough that you can almost map it one-to-one to hardware structures. So we also did characterization at this level. One of the advantages of characterizing at this level is that things like loops, which compilers pipeline, tend to be, for some applications, you can simplify away some of the loops. For some, you even create more because you don't want complex loops, but you create more loops that are simpler. So the Alterra SDK, as far as we know, is based on LLVM. So we build a Clang/LLVM tool that does characterization at the intermediate representation level. So this is what it looks like. Again, the kernels are the application. So you have the number of basic blocks. So the number of basic blocks is important because from the compilers we've seen, it maps one software basic block into one hardware model. So it gives you an idea of how complex it will be on the FPGA. The number of instructions gives an idea of how long it's going to be, so because there's almost one-to-one mapping. The number of loops are important because that is most FPGA compilers try to pipeline your loops because that's the only way you're going to get performance increment. So as you can see, this one is really, really complex, and this one as well. So our case study was to see if you take CPU code, OpenCL CPU code, put it to an FPGA compiler. What is the experience? Do you need FPGA experience, or will it just be as if you're compiling to another CPU or GPU? So remember, we didn't modify the OpenCL code for FPGA. That wasn't the idea. The idea was to evaluate the experience. Would someone, for example, in the biology department who's doing gene matching be able to write OpenCL code for FPGA? That was the sort of thing we are looking at. Because in the University of Manchester, the computer science department often recommends for other departments how to speed up some types of computation. But they themselves still do the coding. So when you're doing recommendations, you have to be sure that they can manage the tools by themselves. So synthesizing the benchmarks, we use Alterra SDK, OpenCL SDK, the latest one when we did it. It was 14.1. And we are targeting an Analtech board. So it's basically, it looks more like there's not much of a difference installing it than installing a GPU. And it has 8 gigabytes of RAM. And it's 8-lane Gen 3 PCIe. And it has this I believe is, when it came out, was the top range of Alterra's FPGA. So this is what the summary of synthesis looks like. So synthesis, when I say synthesis, I mean compilation. So in the hardware world, it's often called synthesis. So I'm going to use that term. So if you notice, two of them failed. There was issues with compiling down to Verilog. However, if you compare it with the last major release, you can see a lot of improvement. So there's almost a twofold improvement without doing anything. So that's an advantage of having a benchmark. So without the benchmark, we'll have spent time trying to see if we can get them to compile. So hopefully in the next major release, they will all compile. Oh, all right. Fair enough, I will try when I get home. So since we already have something running on CPU and something running on FPGA, why don't we go ahead and do comparisons? I must say that, remember, this wasn't optimized for FPGAs. So another thing to remember is that some of the applications failed even after they were synthesized. So 3 of them produced incorrect results, even though they were able to compile. We don't know why yet. 2 never finished executing, so they keep running and running. Okay. So the CPU platform we're comparing, the FPGA card I showed earlier, is basically a Xeon CPU. And it has 16 gigabytes of RAM, and I think that was the latest Intel OpenCL compiler when we did the experiment. So this is what performance looks like. So on this axis is execution time, milliseconds. And if you look at this, you will notice that this is referred as PCI, so you do PCI transfers. So there's an overhead. But generally, if you discount the PCI overhead, FPGAs tend to do better because less is better here on the green part. But for example, Blowfish is so much slower because the loops were written for CPU and the FPGA compiler couldn't unroll it. So compiling things was straightforward, but getting performance, you have to do some heavy lifting. So you have to rewrite some of your applications to target FPGAs. How many minutes do I have? 20?
You have 30 minutes.
Oh, okay. So we have time for questions now. Yeah. All right. Okay, so it's straightforward to compile software, CPU code especially, to FPGA, on what we have seen on Alterra tools. Another thing we have done is that you have to tune some of your kernels, especially if they're complex. So our conclusion is that the compiler is getting better. So we are working on CHO 2.0. So we are adding data parallel OpenCL kernels. And this time we're trying to do proper performance comparison. So we're going to tune for CPU, tune for GPUs, and tune for FPGAs and see which one is faster and try and measure performance in terms of power and energy. And if you've noticed, the applications are not that modern. So I don't know someone running implementation of double precision on GPUs. So it's common benchmarks in the hardware world, but it's kind of useless for most software people. So we need to add what software people normally write for GPUs especially. So we are thinking of doing something in the form of dwarfs, the 13 dwarfs. So have a large coverage of types of parallel computing patterns and see which one fits FPGAs and which one fits GPUs. Remember, sometimes the advantage of FPGAs is not really speed up, but power efficiency. So you might not be that faster than GPUs, but you might be much power efficient. And that's it. So questions?
Okay, let's take our speaker.
Yeah, I have two questions. Can you bring, first question is regarding the chart you show on the PCIe. There you go.
Yeah.
And I just want to understand better the orange portion. You said PCIe. Did you actually distill the time dedicated to just PCIe, or did you also include all of the NQ read and write?
No. I was using the OpenCL events, so it was measuring the actual time for transfer.
So it's a transfer time.
Yeah.
From the OpenCL profile API that you actually measure.
Yeah.
Okay. So which means it is the read and write time. It's
Sorry?
not just it is the actual read and write of the buffer.
Yes, but
Okay.
most of them is PCI from.
Right, but not all of them. So
Yeah.
my question was, I wasn't sure if you actually gone in and separate the two of really the time that's dedicated just to PCIe over here.
Yeah, but
I guess not. So it's
yeah.
okay. I think you answered the question.
Okay.
That's fine. And on the second question is on those lists of application that you had, I would imagine some of them are fairly big. You had it. There you
This
go.
one?
Okay, that's fine. Yeah. So my question is, as on the Alterra FPGA,
Yeah.
there is the report of showing the register size, the memory usage and stuff.
Yeah.
Does any of them kind of go over
No.
the allocated size?
Okay, let me show you this one. Oh, sorry. So all these ones compiled and fitted on the FPGA.
So it did
But-
fit.
Yeah, but it took longer because they had to do some magic to make it fit. The really bad ones took about 5 hours because it was nearly up to the maximum for the FPGA.
So, and can you elaborate a little bit more on the JPEG and motion? You say front-end error. Do you mean that because it doesn't fit or because there was error in the synthesis?
No, it didn't even get to the synthesis stage. So the LLVM front end, which is what Alterra uses, I believe, failed because we think the memory access patterns are too complex for you to understand.
So is that implied the register usage is way too big?
It's not really register usage. The way it accesses the RAM is too complex for it to map. I believe there are some certain types of memory design you instantiate. I think they are too complex for it to handle, so it just simply gives up.
Okay, got it. Okay, thank you.
So if you rewrite it, it might work, but that's not the aim of the whole exercise.
I'll let Simon ask a question.
For your performance results, the CPU, was that running the OpenCL on the CPU?
Yes,
So that would have been using all of the cores and all that kind of stuff on the CPU.
but it's only running more like a single thread, so there's no much core to use. So because we started out from
Oh, I see. Okay.
Yeah.
So even so, it's the
Sorry.
OpenCL, but it might have still been
Yeah.
single-threaded.
Yeah, it's like a task parallel, but we only launch one task.
Yeah.
Because we started out from C, and we also wanted to compare C and OpenCL and see the difference between
Yeah.
the tools and the languages.
Yeah.
So that's
you-
why we want to do a proper data parallel one. Because one of the things why we didn't want to spend time parallelizing them was that the feedback we got earlier on was that you don't normally run this type of applications on GPU. So there's no need parallelizing things like floating point addition.
But I think it's always really important, especially when you benchmark against a CPU. You really should compare against using all of the cores. Otherwise, you've kind of penalised the CPU massively, which is kind of a bit of an unfair comparison. Then, so when you go on to these next stages, it would be really good to do best as possible on the CPU. Versus the best that you can achieve on the FPGA, and that will help us all. I think we're all really interested in seeing how far you can go with OpenCL and FPGAs, and it's hard for people to get a grasp of it. So if you can do us some really nice, fair, apples to apples comparisons as close as we can get, that will help all of us. I think really start to evaluate them.
Okay.
Yeah, I mean, you mentioned something also about doing performance comparisons based on the energy efficiency.
Yeah.
So Simon's done some of that, and that would actually be really interesting if you put that in, so that you had some, come up with a metric that shows kind of that part of the story.
All right.
So you're using the 1.2 SDK for OpenCL?
I think it's a 2.0, but we don't have a 2.0 compliant hardware.
Right. So, but do they support the pipe object? I think they do.
They do, but we didn't.
You didn't use it.
Yeah,
Okay.
we didn't do that.
Because we've tried that, and we actually are competitive. Your numbers are very low.
Yeah.
We're competitive with a fairly decent size GPU
Okay.
for full applications.
On CPUs.
No.
Okay.
FPGAs.
Okay. Oh, okay. You're talking about
On the same
FPGA.
device, on the Stratix 5.
Okay.
Yeah.
So, are you talking about channels, which is what Alterra calls it?
Yeah,
So,
yeah.
Okay. Okay, I understand.
For the 101X series,
Yeah.
we use a render extension, which is the channel.
Right.
Okay.
But with the pipes, we just put our channel underneath the pipes.
And
Oh,
it works
okay.
really nice. Yep.
Any other questions?
Hi,
Yeah.
my name is Rashid. I'm from IBM. My question is that did you try to do any automatic pipelining that Cortis tools usually allow you, or you just ran the straight stack of OpenCL down to the Alterra binaries?
I think the Alterra tool will try to do all the pipelining for you. Then it will give you a report that will tell you the reason why some of them didn't, some of them weren't successful. So one of the things we noticed, if your loop bounds are dynamic, you won't be able to pipeline it. So it's all automatic, so you don't need to do any manual program, things like pipelining. You just give it OpenCL, you wait a few hours, then you run, which is what most people want. I don't think the average user wants to start doing PCI Express and doing pipelining by hand, doing back pressure.
So let me clarify here. We don't need any paragraphs or directives or anything else to make things happen. We have heuristics that are built in our built-in. This is this complex access pattern. What we will do is we will analyze it so that we automatically cache and vectorize. You don't need to guess. We can do all of that automatically. So for an ND range, we will pipeline. That's a given. And flat loops were necessary to get it. And we don't have any instruction to do so. For a task, we use the pipeline. And for as far as including the same pipeline. But we want to keep it as software friendly as possible so that you don't have to come up with all those pipelines and next directives. Just do it.
Okay. Well, generated another question. I think we have time.
Yeah, just a comment, follow up what Doug was saying. Yeah, it is very true that you can just put in and it will run, but you do need, if you want higher optimization, you have to do, depends on range. It could be as simple as some pragma, changing the workgroup size, which I've done and speed up at 2 or 3x right there and there, which isn't that much effort. Or you can do full-fledged and just optimize the whole thing out of it. So yeah, it will work, but given the architecture difference between GPU and FPGA, you really need the hardware, the understanding of hardware architecture to maximize it.
So the question is, will an average programmer, will the average programmer be willing to learn another architecture? Because he already has GPU now.
It's more unlearned. For instance, with a GPU, as we all know, you will pay very careful attention to the workgroup size because you need to make sure that you have 1,024 threads per
Yeah.
block and 1536 and so on and so on. With Alterra, you don't have to do that. We have unlimited cache local memory, and we automatically are going to break it up as needed based on your access pattern. Again, you don't need to split and repartition and resize. We do that automatically based on your access pattern, and we build the local memory as big as it needs to be. So the only thing that you need to be concerned about is my workspace or my work group too big so it doesn't fit on the device anymore. As long as it fits on the device, you'll be fine. So undo all those work groups that you did for the GPU
Yeah. Another thing I find useful is to specify the required workgroup size, because it kind of gives you a custom hardware. So if you don't, I think it does 256, which sometimes you don't really need.
Okay, we better move on to our last talk. Let's thank our speaker again.